started with the go ahead and get started with the introduction. So welcome everyone. I'm Sean Maxwell. I chair the ARMA Induced Seismicity Technical Committee, and along with Jens Snee and Madi Haddad, we welcome you to the monthly webinars on induced seismicity. So today's webinar will be given by Rebecca Salvage from the University of Calgary. So Rebecca gave a version of this talk at the ARMA Symposium back in June, a really interesting case study. So we've invited her to give her some more time to go into a little bit more detail of this interesting case study. So with that, I'm going to pass it over to Jens to talk about the upcoming schedule.
Okay, thanks, Sean. Yeah, we have 3 presenters lined up and more being added all the time. And so next month, October, note the different date. It's not the first Friday, it's Friday the 15th. Alexandros Savaitis from the Texas Bureau will be presenting talk title to be determined, but quite likely about induced seismicity in Texas. The following month, again, the first Friday of that month, 5th of November, Sherilyn Williams-Stroud will be presenting about the induced seismicity from seismic data at the Decatur, Illinois carbon capture and storage site, which has been largely a success story from an induced seismicity standpoint. And then early December, the Friday the 3rd, Sergei Shapiro has just agreed to present, and so I think that'll be of a great deal of interest to people because he, as many know, developed one of the key models for predicting induced seismicity associated with fluid injection.
Good morning, everyone. This is Mahdi Haddad at the Bureau of Economic Geology. First of all, thank you so much for joining us this morning for another great webinar by Rebecca. For the people who haven't attended our previous webinars, there is a refreshment here for the general rules for this webinar series. First, feel free to share the webinar invite to interested parties, and also you can contact the organizing committee, me, Sean, or Jens for adding them to the distribution list for future webinars. And everyone will be muted during the talk for better flow of the webinar. And please submit your questions during or after the talk in the chat button at the bottom of the Zoom meeting window. Please send these questions to everyone. And this specific Zoom meeting is recorded. Not necessarily all webinars will be recorded. We ask the presenter for the permission to record. And also, previous recordings have been uploaded to our YouTube channel. Link to the link is within the invitation email. Please subscribe to this channel to receive notifications for the future uploads. This webinar series is in one of the technical webinar series of ARMA for the community engagement in this association, American Rock Mechanics Association. I have prepared a poll. I would appreciate it if you respond to the questions in this poll in order for us to understand what is more of your interest for attending the symposium of ARMA or servicing you better in the future. So I'm running the poll right now. You can just answer the questions and submit it whenever you are available, and then you can close the window. And after the webinar, I will announce the results of that. So do you see the questions? I just launched it.
Yeah, I see it, Madi. Thank you.
Okay, great.
Do you have a prize for the poll?
There is no prize. It's just we just would like to know your opinion, the community opinion, and then we can better service them. Actually, that would be a mutual benefit for both of us to run ARMA as a bigger community of rock mechanics, as well as this webinar series. So without further delay, let's invite Rebecca to take the stage for the presentation.
Thank you so much. I'm just trying to end the poll. There we go. Perfect.
Okay.
Okay. So, I hope everybody can see this. So thank you very much, Marty, Sean, and Hens for letting me present today and for the invitation. It's a real pleasure, and given the what I would say in British would be the number of big cheeses that have been before me, it's quite some shoes to fill. So I will do my best. As Sean mentioned, I gave a very brief version of this talk at the ARMA symposium over the summer. So they were limited to sort of 15 minutes. So this is going to be sort of the extended version of that. And what I'm looking at is I'm a postdoctoral associate at the University of Calgary, mostly focused in induced seismicity. I dabble a little bit in DAS these days, but my background is seismology mostly. And today I want to talk about a really interesting case study from 2018 that we have been researching, which looks at how transitional stress regime may influence induced seismicity. And the area that I'm particularly interested in is in Northeast British Columbia in Canada. So I obviously I have many co-authors, which will be acknowledged right at the end, but David Eaton is my main supervisor, so I just want to acknowledge him for all of his help and support for doing this. So I'm just going to sort of start kind of really broad, I guess, with some of the big questions in induced seismicity that sort of that I think about, and that certainly in the areas that I'm interested in Canada seem to really be questions that we, as of yet, haven't been able to answer. So something that we see in the areas that I'm interested in is why are certain wells seismogenic and others appear not to be at all? I'm not sure I can answer any of these questions, and I certainly won't be attempting to answer any of them with this presentation alone, but it's just sort of one of those questions as to why we don't always see seismicity. And more recently, it's kind of become apparent that aseismic processes may be playing a key role in induced seismicity. And so how do we really understand how induced seismicity is generated, and what are the sort of the ways in which all of the generation methods that we generally talk about, how do they sort of interact with each other? Something which has come out of this work is that why do some induced events have long precursory sequences and others almost none? So the events that I'm going to talk about today had very little precursory sequence. So how do we use that information to help with the mitigation of induced events, and also for monitoring of our sort of hydraulic fracturing or disposal wells? How can we do that? So and finally, the best way to mitigate this induced seismicity, it's obviously for us researching it, it's an interesting phenomena, but for sort of the general public, officials, government, and even the regulators and the operators themselves, it's something that we want to try and avoid as much as possible. So I just wanted to go over really briefly about historical seismicity in Western Canada. For those of you who may not be entirely familiar with it, I'm sure some of you are, but so I'm based in Calgary here, and we have the Rocky Mountains sort of spanning up here. So most of the seismicity in Western Canada is based off the subduction zone off of the coast, so close to Vancouver. But what you can see since 2009 is that there are these sort of isolated hotspots, I guess, of seismicity that have been ongoing. So we're interested in these because they occur almost not in relation to anything else, and we do believe that the majority of the seismicity that's occurring sort of here and And here, for example, is anthropogenic. So this is something which it's not a concern is the wrong word to use, but it's something that we need to look at and to be aware of, right? So the area that I'm particularly interested in that we're going to talk about today is here. So it kind of sits right on the border of Alberta. So this is Alberta here, which Edmonton and Calgary, and British Columbia, which is where Vancouver is. And it's an area which has undergone significant amounts of hydraulic fracturing in recent years. So just to sort of draw our eye in a little bit more to this sort of area, this is the Montney Play that is being developed for unconventional resources. We know that the seismicity, which is shown as sort of gray dots, is very spatially concentrated. It occurs in very distinct areas, and it also occurs in very temporal clusters, so related to ongoing hydraulic fracturing and disposal. I'm showing the sort of very
I mean, it's a webinar. But...
well, not sparse, but there's a public monitoring network led by the government of Canada, which you can see as these black triangles. And there are a number of distinct monitoring or what are called regulatory areas. So the area that I'm really interested in that we're going to talk about today is called the KMISMA, which is outlined in orange here, and it's known as the Kiskatona Seismic Monitoring and Mitigation Area. This area here is a separate area, and the reason that we have these distinct monitoring and mitigation areas is it allows regulators to impose certain rules on those operators in this area. Something that I'm going to sort of touch on briefly is about structural corridors. So something that I think a lot of us have maybe had issues with, I guess, in the past is this whole idea of faults being single continuous entities. I think we can all agree that faulting in a lot of areas and in the real world is much more complex than that. It's unusual that you get a single continuous linear feature that extends for miles and miles. So something that we've been working on at the University of Calgary is to try and put faults into what are known as structural corridors. So these sort of red areas here, which delineates that faults within this sort of area act in sort of not in a single motion, but they can all sort of be grouped together. And this area here is tectonically active due to the faults here. So just to give a very sort of brief overview of what's been happening in the Montney Play, for those of you who may not know, since 2005, the number of producing wells in the Montney has increased rapidly. So this goes to 2019, and you can see that the number of wells which are producing are shown as orange bars, and the total number of wells is this blue line. So as of 2019, there are over 3,500 actively producing wells in the Montney Play, and this has been sort of correlated, or at the same time, we've seen an increase in Northeast British Columbia in the number of magnitude 3s events. So since 2005, which this represents 2005 to 2019. So I've just tried to highlight the same sort of extent here. We've seen a rapid increase in the number of magnitude 3s. So kind of like a hockey stick, I guess, would be the equivalent. So this is a cause for us to sort of investigate this and to try and to better understand how we can mitigate these kind of issues and how we can better understand why they're happening and what the consequences of them are. So just to sort of talk about the historical seismicity in the KMISMA in general. So I'm going to talk about 2018. This is a map that shows the density of seismicity in 2018. The event that I'm going to talk about is labeled here. So it was a magnitude 4.5 in 2018. The events, the figure on the right shows 2020. So, and in 2020, the University of Calgary actually installed our own monitoring network, which is shown by the yellow triangles. So it's feasible that the number of events here, we have a lower magnitude of completeness compared to 2018. So we're capturing many more smaller events than we were. But what's interesting in the KMISMA typically is that seismicity sort of appears spatially to run in a sort of northwest, southeast orientated corridor. And there are a number of sort of distinct areas, I guess, which have had a lot of seismicity in recent years. So we can see in 2018 that Farmington was an area where we had a reasonable amount of seismicity. In 2020, the sort of most active area in terms of seismicity was actually close to Tower Lake. So it's not as if all of the same areas are being activated year on year. So just to talk about the regulations within the KMISMA, as I said, it's a distinct monitoring and mitigation area. And the reason that it was sort of brought into place was that a special order was issued in 2018 by the BC Oil and Gas Commission, who is the regulatory body for British Columbia. And they noted that seismicity in this area was a cause for concern. So with this special order that was implemented in 2018, there are a number of things that operators in that area now have to do on a regular basis. So they have to have a pre-assessment of the seismic hazard before they start any kind of work. They have to notify the residents. They have to have an accelerometer within 3 kilometers of the active well. And they have to monitor it using a real-time seismic array. So this sort of all comes down to the fact that in Alberta and British Columbia, we operate a traffic light system for our hydraulic fracturing and our operations, like many places around the world. So within the KMISMA, the red light, traffic light, where you have to suspend operations immediately is a magnitude 3 or greater. So anything that is a magnitude 3 or greater automatically means that all operations need to be suspended. If anything goes above a magnitude 2, then they have to implement their pre-prepared mitigation plan. And this is different from other areas in British Columbia where the suspension for operations is a magnitude 4. So this area is much more carefully controlled and monitored for induced seismicity, because we've seen such an increase in the number of events and in particular the number of felt events within this area. So just to briefly talk about some of the monitoring that goes on within KMISMA. So as I said, in 2020, the UFC actually installed our own network within KMISMA. So they're shown as the yellow triangles. We also installed 2 co-located accelerometers shown by the hexagons around the triangles. And this data does flow to IRIS with a 91-day embargo period. And after that, it is completely downloadable by anybody in the community. So anybody can go in and look at this data. It's, like I said, it's been active since January 2020. So actually the events that I'm going to talk about were in 2018. So we did not catch them, obviously. And the data that I'm going to talk about comes from a private network that was installed at the time. But there are also a number of public stations which are utilized not only by us as researchers, but also by operators in the area. And the KMISMA typically, I would say, has a generally quite reasonable coverage in terms of sensors and seismometers. So we are capturing a large majority of the seismicity that's going on in this area. And just to show you what sort of I get privy information to of the real-time monitoring that goes on within the KMISMA. So we're collaborating with Nanometrics, who offer us a portal, which is fantastic. I pulled this yesterday. So we can see that you get sort of the magnitude and the locations of events and the timing of the events. So it's a really great tool for us to be able to understand in near real time what's going on within this area. So as I said, since we've installed our network, we had sort of just over 13,900 events as of yesterday that we've managed to detect within the KMISMA, and magnitudes range from negative 0.7 to 3.4. So we have had a number of red light events since our network has been installed, but not on the scale of the events that I'm going to talk about in a minute. The depth of the seismicity is typically coincident with the Monty Formation, which is what they're targeting. And again, the seismicity occurs in this northwest-southeast corridor. So it's a great tool that we now have access to for 2020 onwards, for understanding sort of how these events are generated, and also how faults are being activated within this area. And the study that I'm going to talk about now is sort of I guess was one of the sort of precursors to us thinking that this might be a good idea to install this network, because we managed to understand certain things about the seismic sequence that I'm going to talk about, but other things were not as clear to us. And the idea of being able to have our own network and access to our own data was therefore really appealing. And we have been able to, on a number of occasions, in almost near real time, watch as rig operators have appeared to fracture very linear wells, and we've been able to sort of follow that in near real time. So it's a really great tool that we're able to utilize. So I'm just going to briefly talk about the structural setting of the KMISMA, because this is going to be really important to what I'm talking about. The KMISMA area lies between Fort St. John up here and Dawson's Creek down here. And on this figure on the left-hand side, I've plotted not only the sort of the known faults, which are shown by the black dotted lines, which are taken from mostly from Carolyn Furlong's paper in 2020, but also some other seismic, 2D seismic lines, for example, and things like that. And I've also plotted on top of that the work of Paulina Wozniacka in her GSC Open File report of the structural corridors. So you can see that the structural corridors line up really nicely with most of the seismicity that we're observing in the KMISMA. And the KMISMA is a really kind of a complex place, I guess. I'm sure there are plenty of other complex places in the world, but we've known since sort of the 1990s that it's an extremely complex place. It's dominated by what's known as the Fort St. John Graben, which is sort of is represented by this kind of large northwest southeast corridor here. And this was sort of generated, I guess, in the Carboniferous sort of Permian time. It's a half graben complex, but it has since then been reactivated. So we also get asides from the sort of the typical normal faulting within this area, it appears that there are a number of strike slip faults which sort of separate individual normal faults. And also these normal faults, which I've sort of highlighted in red here, typically often become reactivated with the seismicity that we're seeing in the KMISMA in recent years as reverse faults. So it's kind of a really complex area. Other things, I guess, to note is that we're not too far away from the sort of fold and thrust belt extent of the Rocky Mountains. So it's possible that that's also having an influence on this area as well. So it's a really interesting structural setting. The Fort St. John Graben, like I said, is the sort of the main feature within this, but there are a number of other satellite grabens that you can see plotted as well, and the area is also, as this figure shows, crisscrossed with a number of large scale, what appear to be large scale faults as well. So that may not necessarily line up with the structural corridors that we've defined. So it's certainly a complex area, which makes the fact that we're inducing seismicity in this area even more kind of interesting. So finally, I'll get around to what I actually wanted to talk about today, which is the events of the 30th of November 2018. So we had a magnitude 4.5 on the 30th of November 2018. It's the largest event that has been registered within the KMISMA. And it occurred about half a kilometer away from an active hydraulic fracturing operation. So the operation was immediately suspended in line with the BCOGC protocol. And we know from very initial analysis that the event was determined to be a reverse focal mechanism. So you can see the USGS focal mechanism here. This was calculated using just public data, so the sort of reasonably sparse public array that was within this area. And Ali Babi Mahani and et al. Suggested that this is a reactivation of one of the significant east-west orientated normal faults within the area, which has been associated with the Fort St. John Graben complex. So something that was really interesting about this sequence is that there were two significant aftershocks. I've put aftershocks in inverted commas here because I don't believe that this event here, magnitude 4.3, was a true aftershock, and I'll explain that a little bit later. But we had a magnitude 4.3 and a magnitude 3.6 within 45 minutes, despite the suspension of all operations. And some analysis done by Pena Castro et al. This year has suggested that the hypercenters range from sort of 1 to 6 kilometers deep. So you can see this is the well. These are the two wells that they were fracturing at the time. The majority of their seismicity lies sort of 1 to 4 kilometers deep, I guess. But they put the largest events of magnitude 4.5 at a depth greater than 5 kilometers and separated from the other events within the crystalline basement. And they suggest that this is possible due to rapid fluid pressure increase along a permeable conduit which connects these two areas. I'm going to show you the work that we've done, which actually puts the magnitude 4.5 within this cluster up here, based on our location results. So we don't think that such a complicated analysis is needed, but in order to sort of explain this seismic sequence. So just want to briefly talk about the available data that we had. So we had continuous seismic data for about 2 weeks, 3 days prior to the largest event and sort of 10 days afterwards, from an 18 3-component broadband seismometers, and it's a private network. So this data is not available. We got it directly from those involved. And you can see the distribution of seismometers as these black triangles. Here is the location of the largest magnitude 4.5 event. Plotted, you can see that it lies almost directly along this sort of east-west orientated normal fault. And we think that this sort of distribution of sensors here, we've got a all within the hypercentral region is allowing us to sort of get better understanding of the seismic sequence that we see here. So I'm just going to talk quickly about how I went about detecting the seismic sequence, taking up locations, and et cetera, et cetera. So I used RedPy, which is a repeating earthquake detection software written in Python by Alyssa Hovertok-Eller, who is in the USGS. She created this software so that it uses a simple STA-LTA algorithm, and you can set a number of parameters such as, how many stations you want to coincident trigger on, and how much correlation you want between events, etc. So using this over the sort of 2 weeks worth of data, we identified 64 events. And then we took those 64 events and we used a template matching algorithm in order to try and further populate our catalog. And the template matching algorithm that I used is called EQ Core Scan for anybody who is interested. Again, it's written in Python. And so using both of these, this combined approach, we ended up with just over 560 events within these two-week period. So if we look at the sort of temporal evolution of the seismicity over these 2 weeks, the red dotted line here represents the magnitude 4.5 event. This upper plot shows the injected volume of fluid in the northern and the southern well, respectively, up until the point when they had to cease operations due to the magnitude 4.5. The second plot down shows the hourly event count with time. And the third is the magnitudes of events, and the fourth is the frequency index. So the frequency index is kind of an interesting parameter which tries to relate the amount of high frequency to low frequency energy within a waveform. So the idea is that the lower the frequency index, so below 0, excuse me, events that have a frequency index of less than 0 are dominated by low frequency energy, and those higher than 0 are dominated by high frequency energy. So the sort of high and low thresholds are user defined. So you can always sort of mess around with that as well. But just a few things to point out about what we observed in the temporal evolution of the seismicity. So first, there was almost no precursory seismicity. So over the sort of about 3 days, 72 hours prior to the largest event, the magnitude 4.5, we had 74 events. So really very few. We didn't really see a rapid increase in the seismicity prior to the largest event. So this is interesting because almost all mitigation schemes around the world for hydraulic fracturing are based on the thought that you get this precursory seismicity, which then allows you to mitigate for the big one, so to speak. So we didn't really see that in this case. And something kind of strange happened. So following the largest magnitude 4.5, we got a sort of a typical decay in the number of seismic events with time that you would expect. But then 16 hours later, we got this massive increase in the number of events. So we saw over 100 events within a kind of a 20 to 30 minute period that completely then died off almost immediately. It's interesting to note that this sort of 20-minute period that we saw 16 hours later also included a number of higher magnitude events, I guess. They were not obviously as large as the main shocks, but they were significantly higher than most of the events within the sequence, which kind of fall around 0.5 to 1.5 or 2, I guess. So this is kind of interesting, and this also corresponds with a rapid decrease in the frequency index, which indicates that the waveforms within this sort of 30-minute period were dominated much more by low frequency energy, and there have been some recent studies that talk about the low frequency content of waveforms. I come from originally a volcano seismology background, and in that setting, when we have very low FI index, we typically attribute that to fluid moving through the system, whether that's gas or magma or water or any of the above. So it's interesting that this period of seismicity was also associated with this sort of lower frequency index, as was the largest main shock of the sequence here. So they're just some observations that we've noticed, which seem kind of curious. So let's talk about those aftershock sequences. So following the magnitude 4.5, the events typically follow an Amori type decay that you can see here. And I mentioned that one of the events within the 45-minute period following this magnitude 4.5, I didn't believe was a true aftershock. You can see that here. This is the magnitude 4.3 event. It's a massive outlier to our sort of typical Amori decay plot here. So I'm sort of suggesting that maybe there were two main shock events. They were very close in time, and obviously this event of a magnitude 4.3 following a 4.5 doesn't follow Barth's law, which we typically would invoke for aftershock events. So it's kind of curious. There have been other instances of double main shock seismic sequences, but they're not generally that reported on. So it's kind of a curious thing. But I personally think that this second event, the magnitude 4.3, is not a true aftershock. And then if we look at the second strange rapid increase in seismicity 16 hours later, like I said, we had greater than 100 events over a 30-minute time period, potentially associated with a decrease in the frequency index, which you can see plotted on the bottom here. Another curious thing is the magnitude pattern with time. We saw that the events sort of started with a large, well, not large is the wrong word to use, but a larger event, and then decreased, and then kind of picked up again and went back up to greater than magnitude 3 events, and then came down. So it's just a curious pattern that I've not really seen observed elsewhere, and I'll give you the spoiler now. I can't explain it. I don't know why this is happening. I don't know why 16 hours later we had this rapid increase, but it's just a curious phenomenon that we observed with this data. So we then went about locating our events. I manually picked 64 of the events that were identified by RedPy. Any geophysicist will know that manual phase picking is a key part of the job, but it's certainly not the most enjoyable of the jobs that we do. So I then automatically picked the remaining 500 events, because I wasn't going to sit there and try and manually pick 550 other events. So I used a cross correlation methodology in order to do that. And we then determined the high percentages using two programs which are fairly well used, I think, within the industry. So non-in-lock, which is a probabilistic global search algorithm, and then HypoDD for relocating double difference algorithm. And just to sort of tell you that we used a 1D velocity model, but one that was specifically calibrated for the KMISMA. So it's calibrated using sonic logs, formation tops, and previous seismicity from the BCOGC, so the British Columbian Oil and Gas Commission, the regulators. And this is obviously specific to KMISMA. The velocity models in general for sort of Canada, British Columbia even are very non-unique, I suppose is the word to use. So we were very lucky that we had this specifically calibrated KMISMA velocity model. So I'm going to focus from here on out on just 91 hypercenters. And the reason that I'm doing this as opposed to all 500 is one, we believe they're highly reliable. They had a high cross-correlation coefficient with the template events. So when we were trying to detect them from the continuous seismicity, and they also had greater than 5 phase picks per event, which allows us better constraint on not only the hypercenter location, but in a few minutes, I'll talk about vocal mechanism determination and source characteristics. So, you know, having the number of phase picks greatly helps in that. So you can see the events are color coordinated here by time for these 91 events. The small little black C, I guess, is the wells that were being stimulated at this time. And we can see that they form a really tight cluster, very close to this, this well that was being operated. And they almost lie directly upon this east-west normal fault, which is associated with the Fort St. John Graben complex. In depth, we see that the events cluster typically are around the horizontal part of the well where they were stimulating. The fluid injection interval is about 2.25 kilometers, and the largest events, which are shown in blue here, that occurred on the 30th of November, occurred at about 2.5 kilometers depth. So, you know, they're very close to the fluid injection interval, which you would kind of expect. Something that is kind of interesting is that we didn't see a clear spatial evolution with time. So we didn't see the events migrate away from the well. We didn't see them you know, spatially migrate in map view either, or in depth. So they seem to all be really concentrated within this this level in this area, which is interesting when we're trying to explain the generation of such events. So just to look at the magnitudes, we followed the local magnitude calculation for the KMISMA, which was determined by Ali Babu Mahani and Hon Kao, and it uses the Wood-Anderson amplitude simulated, but for the vertical component, which is not always the component that is used when calculating local magnitudes. So we can see that this is for all of 565 events. Our magnitude of completeness is about 1.1. But we did see a number of events which are much, much smaller than this. And we had 416 events greater than the magnitude of completeness. The B value is interesting. The B value that we calculated is really low. Typically, B values for hydraulic fracturing experiments, you know, that we've seen in the literature that they can range greater than 2. Sort of natural seismicity typically sits around 1, we believe. So this is really quite curious that the B value is so low. There is some work that was done in California, which suggests that B values of sort of 0.7 are associated with reverse and thrust type regimes. And actually that is what we see here, but it's curious that a hydraulic fracturing experiment would give us such a low B value. But it is, possible that what we see here is a multimodal B value. Our histogram isn't what I would describe as a typically very nice histogram. We don't have that typical slope of the B value, and that certainly appears to be affecting our calculation here. There seems to be two populations of events, those which are sort of less than 2 and those which are greater than 2 for the events in this sequence. So this is just a description of the source, how I went about calculating the source characteristics of events. We used the Bayesian approach for moment tensor inversion, which was derived from MT-FIT, which uses p-wave polarities and estimates the moment tensor in both a double couple and a full moment tensor space. And we then took these events and undertook a stress inversion using the derived focal mechanisms to invert for the stress tensor, as has been described by Vavricek. So this is the method that we used. So there are a number of assumptions that go into all of this, in particular the stress inversion. It assigns the fault plane as opposed to the nodal plane based on the highest Morkelin failure stress. But it does allow us to determine not only the orientation of the principal stresses, but also sort of a relative magnitude of stresses, which is known as this R value. So small R values indicate that sigma 1 and sigma 2 are close in magnitude, and large is that sigma 2 and sigma 3 are close in magnitude. And that's going to be important for the discussion of these results. So just to look at the two largest events, the magnitude 4.5 and the magnitude 4.3. I guess reasonably surprising to us, and maybe to you guys as well, is that they're completely different mechanisms, occurred within 45 minutes of each other, occurred very close spatially, completely different. So this is just one of those things, and actually when we look at the whole data set, we can see that that we've got a really large variety in the focal mechanisms anyway. So we managed to derive 72 focal mechanisms from the original 91 hypercenter locations that we saw. The reason that we weren't able to determine all 91 is pretty much due to focal coverage on the sphere, determining the p-pic polarities, etc., etc. So we had to discard a number of them. But you can see here from this figure, this is just a really zoomed in version. Here are the wells that were being operated. Here is the fault that the east-west fault, which is associated with the Fortson-Graben complex. We can see generally that the whole sequence was dominated by reverse events. So those are shown in blue. Normal events are shown in green, and those which are dominated with strike slip are shown in purple. So we can see generally the seismicity is dominated by reverse events. We did see spatial differences in terms of the seismicity. So I split this up into 3 sort of spatial areas. The northwest is pretty dominated by reverse, and in fact these reverse focal mechanisms were typically all low angle, so I would call that a thrust event, an event where it's a low angle thrust. In the northeast, which includes both the main shock, which is shown here, and the largest aftershock shown here, typically was dominated by oblique reverse events, but you can see there's a mix of also some normal and some strike slip thrown in there for fun. This area in the south, very few events. I think there were 7 events within this really small cluster down here. and they were dominated by this oblique strike slip sort of events. So we can see that typically the seismicity was generally dominated by reverse events, and this is in agreement with the earlier work of Ali Babu Mahani, who suggested that the main shock event was a reactivation of this what is believed to be a normal east-west trending fault, but reactivated as a reverse event. So if we look at the inferred state of stress, so I'm taking all of the events before the main shock here and after the main shock. So the main shock I'm determining here as the magnitude 4.5 event. We see that generally we have well-constrained principal axes, but something that's really interesting is that following the magnitude 4.5 event, we got about 30 degrees counterclockwise seismic rotation of sigma 1. So sigma 1 is shown by red here, following the largest event. And the direction of sigma 1 following the magnitude 4.5 is actually more consistent with the SH max direction from the world stress map in this area, which the closest measurement is taken from a borehole breakout, and it's not amazingly close in terms of location, but close enough in terms of the stress map. And something that we think is quite interesting is that we saw a reversal in sigma 2 and sigma 3, so shown as blue and green, following the largest events in magnitude 4.5. So sigma 2 here goes from being pretty much horizontal to near vertical, and the opposite for sigma 3. If we split up the stress inversions based on those three groups, so sort of northeast, northwest, and south, things obviously get a little bit more complicated. It's not quite as nice looking, but overall we see that sigma 1, which is shown in red on these figures, is typically horizontal, does appear to rotate. For example, you can see in group 2 here we have what appears to be a significant rotation following the main shock. So these three here represent before the magnitude 4.5, and these three here are following the magnitude 4.5. Something again that we can see, but probably not quite as clearly, is that sigma 2 and sigma 3 are variable in orientation and in direction, but they do typically appear to change following the magnitude 4.5 event for each of the groups that we've seen. And if we calculate the R value, which is the relative intermediate principal stress magnitude, when we look at all the events, we get an R value of 0.75, which suggests that sigma 2 and sigma 3 are really similar in magnitude. And when we calculate the R value based on sort of all of these groups, we can see that there's a significant change following the magnitude 4.5 event. So when I say the R value here for all events, I'm talking about, it doesn't matter whether they were before or after the main shock. This is every event that occurred within the sequence, so all 76 focal mechanisms. Here we've split all as being sort of those before and those afterwards, but just to see the difference in change in the R value over time based on that magnitude 4.5 event.
Hey, Rebecca, just quick time check. If you could kind of target to wrap up in the next 5, that'd be great.
Yep, that's fine. Yeah, no problem. So just to briefly talk about the expected maximum magnitude of the events. I'm sure many of us are pretty familiar with this kind of stuff, but our events all plotted above the Magar line and also greater than the Gallus line as well. So based on the total fluid injection, these events were not expected. The magnitude 4.5 event was not expected. So this is interesting because it shows that perhaps we need to do some sort of recalculation of how we understand the expected maximum magnitude from a sequence. So just to sort of go over in summary what we found from this seismic sequence. It's the largest event to date in KMISMA from magnitude 4.5. We had a very complex aftershock pattern. The events appear to be clustered at shallow depths within a structural corridor, the Fort St. John Graben. Bit of a variety of determined focal mechanisms, but typically dominated by reverse. And it seems that there was a significant change in the stress following the magnitude 4.5 event. So not only did we see a rotation in sigma 1, but sigma 2 and sigma 3 appear variable, but with a similar magnitude. And then following the magnitude 4.5, we kind of, the two switch with each other. And an event of this magnitude was not expected based on the current models of fluid injection. So what has this seismic sequence taught us? Not all large events in the KMISMA have a clear precursory sequence. We had 74 events in the first 72 hours, but nothing that would sort of be seen as alarming. Sequences might be able to have two main shocks, as they don't follow Barth's law. And that aftershock generation is a really complex process. And sort of the main takeaway, I guess, from this is that small changes in stress might be able to cause slip on many different orientated faults within the KMISMA. So that comes down to the fact that we think sigma 2 and sigma 3, although variable in orientation and direction, actually have a similar magnitude. So very small changes in stress can sort of slip between the two of them. I just wanted to point out that these structural corridors, I'm not completely making it up off the top of my head. This is a 2D seismic profile from very close to the area, courtesy of pulse seismic. We see that there are a number of faults within a very small spatial extent, and they all appear to sort of affect very different areas. So I think determining a continuous linear feature from seismic is an ongoing challenge, and that we maybe should be talking more about structural corridors which are affecting areas of induced seismicity than single faults. I'll briefly go over this, but what caused the seismic sequence? So I'm split them into two kind of distinct areas, the direct pore fluid pressure and poroelastic phenomena on one side, which is sort of the models that we've had for a long time, and aseismic processes. On the other side, for the direct pore fluid pressure, we know that this event occurred in response to hydraulic fracture